So this video is about chapter 8. It's about nonlinear regression functions. So we already learned OLS, we called it linear regression. And now we will start to think about nonlinearity. So what does this nonlinearity actually means? It means that the slope is nonlinear. Okay, it's about a slope. It's not about any other things. It's not about intercepts. So we set that up first. Okay. So it's just keep that in mind that we are talking about whenever we are talking about nonlinear regression, we are talking that the slope is nonlinear. Okay. Okay. All right. So this chapter we have about 3 parts. The first part is about nonlinear regression functions, its general comments. Okay, and then we will figure out nonlinear functions for 1 variables. And we'll also talk about for 2 variables when interaction happens. And the last part is about an example. We probably will briefly go through that to understand what kind of models is suitable for what kind of situations. Okay. So the regression so far has been linear in the X, which means that we have a regression line that is straight, right? If it's straight, then it's linear. But the linear approximation is sometimes not a good one. And a multiple regression model can only handle omitted variable problems, but not for nonlinearity. So this is a linear model, okay? We believe that test scores and student-teacher ratio probably or maybe has a linear relationship. This linear relationship says that if we increase student-teacher ratio by 1 unit, which means that every teacher teach 1 more students, then the test score is gonna drop about 2.28. We made an assumption here, that is, we think that every student's added into the teacher's burden is the same, right? But is that the case? We don't know. It's just when we plotted this scatter plot, we feel that this is linear. Okay, so when do we feel that it's nonlinear? This plot. Okay, so the test score and income relation looks nonlinear. Okay, in this graph, we can see that there is a blue line that is straight, but we know that this blue line doesn't fit well in the beginning and in the end, right? So let's take a look at here. So see, here the blue line doesn't fit really well, right? We can see a very big residual here because the distance between the dot and the line is getting big. And we also see that here, the blue line also doesn't fit really well, right? Because there is a very obvious overestimation. Does anyone remember what this is called? We call this heteroscedasticity. Okay, what does heteroscedasticity means? It means the variance of errors or variance of residuals differ across the X variable. Okay, you can, okay, it's not really required, but you can have a sense that the residual or the error gets larger and larger at the beginning and at the end, but the error is relatively smaller in the middle. Okay. So what would be a good line look like? If we want a really good line, then it would be a nonlinear line. Okay. It will be a line that has a steeper slope at the beginning, but as the income, the district income increases, the slope gets flatter and flatter. Okay, again, when we talk about nonlinear regression, we're talking about that the slope being non-straight, right? So in this case, the slope will decrease as x increases. This pink line will be what we want to model. Okay, so several elements. Let's conclude first. In this graph, we believe that a linear model might not fit as well. So we want a nonlinear model. And the linearity comes from the slope. The slope is changing with x variable, which is district income. So we want the slope to decrease as district income increases. Okay. And so this is what we want to model. In this case, we'll probably have a better fit of the model. We'll probably, and in reality sense, we probably also have a better explanation because as people, as some district, if they are poor, right? If they are poor, let's say the district incomes is between $10,000 to $20,000, then increasing the district income will make a large difference for the test scores. But as district income becomes higher and higher, which is in those rich neighborhoods, rich districts, then increasing some income probably doesn't make that much difference. Okay, you can think about, let's say $1,000 is more important for a poor person than for a rich person. A rich person might not find $1,000 very important, but the poor person might find $1,000 that matters a lot. Okay, they might be able to afford a lot more educational resources, while those richer districts, they already have abundant education resources. So increasing district income for those in the right-hand side wouldn't make that much of difference. So the slope at here, probably change this. So the slope at richer range is flatter, but the slope at the poorer range is steeper. Okay, so there is several reasons we need a nonlinear model. And now let's take a look at how we actually modeled it. Okay. If a relation between x and y is nonlinear, that is saying that the effect on y of a change in x depends on the value of x. That is, the marginal effect of x is not constant. Okay, the 1 unit change in x is not, the effects of that on y is not always constant across different values of x. So then at that point, a linear regression is misspecified. We call that the functional form is wrong. Okay. If a linear regression is misspecified, then we call that the functional form is wrong. So then the estimator of the effect on y of x is biased. Okay, it is biased because the model is wrong. So we won't be able to get what we want to interpret, right? Because if you interpret the increase of 1 unit of x, which is $1,000, you're gonna say, oh, if I increase $1,000, then test scores is gonna increase for several points. But that is not the case because this effect is not the same across different income range. So the solution of that is to estimate a regression function that is nonlinear in x. Okay. A general form looks like this. That is, y is a function of x1 all the way to xk. Remember, what is the lowercase k? Lowercase k is the number of x variables. Okay. So this will be a nonlinear function, although we still need some of the same assumptions. That is, we want the error, conditional error to be 0. This is the same. We want all of these points to be IID, or we want our sample to be randomly selected. We don't want big outliers, and we don't want perfect multicollinearity. Okay. So the key concept here is that if we increase delta unit, delta x1 unit of x1, then we'll get delta y unit change in y. So delta y equals to the function of x1 plus delta x1, x2 all the way to xk, minus x1 all the way to xk in this function. And we want the change of that to be different in y. Okay. So you don't need to memorize these functions here. So this function, let's say, so this function, you don't need to memorize it. You just need to understand this is how we try to model it. But at the end, we will tell you what kind of f functions is available for us to do. Okay. All right. So here is some functions of a single independent variables that we can use. The first one is called polynomials in X. We can use quadratic qubit or higher degree polynomial to model the X variables. That is the first approach. And the second one is called the logarithmic transformations. So you can take log of x or take log of y, which provides you a percentage interpretation of coefficients that can make sense in many applications. Okay, so we want to take a look at them one by one. The first one is called polynomial in X. Suppose we have X variable, and now we can have X squared all the way to S to the degree of R. This is just a linear multiple regression model, except that the regressors are powers of X. Okay, what does that mean? That means that if you regard these things into something else, okay, if you think of this X as X2, S2, all the way to XR. Okay, so then what you end up having here is, and the first one is X1. Whoops. So you end up having a bunch of variables from X1 to XR, except that X1 is X, X2 is X to the power of 2, and XR is X to the power of R. Okay, my question is, do we have a perfect multicollinearity problem? And the answer is no. Why? Because X to the power of something is not a linear transformation. it's to the power of something. This is not a linear transformation. So you do not have a linear combination of sum of the x that equals to the rest of it. Okay. I think this one is pretty straightforward. Okay. So no, we don't have perfect multicollinearity problem. That's good. So we can just estimate this regression as what we are familiar with. We will just create x1 equals to x, x2 equals to x to the power of 2, all the ways to xr, and then we throw all of them in to run the regression. Okay, so if we want to replicate this with income, and let's start with a quadratic and cubic specification. Then the first one, we have test score equals to beta 0 plus beta 1 times income plus beta 2 times income the square. And in the cubic specification, we'll have income, income square, and income to the power of 3. If we run the regression in theta, it looks like this. Okay, which one is beta 1? Beta 1 is here. Beta 1 is 3.85. Beta 2 is this quadratic term. Okay, this quadratic term is highlighted as in red because it is the extra term that we put into this regression model. It is negative 0.04. And what's important is that it is significant. Okay. That means that our slope does change as we increase our x value, which is average income in the districts. How about beta 0, which is the intercept? The intercept is 607. Okay, we don't really care about the intercept. We just care more about beta 1 and beta 2. If we plot this function, which is the pink function that we want to have, then it looks like this. Okay. So here we put into our quadratic regression and the linear regression, and you can clearly see that the quadratic regression fits much better than the linear one because it adjusts to the linearity in the slope, right? And it gives you a feeling that the slope is steeper when the income is lower, and the slope is flatter when the income is higher. Okay. Okay. And if we use this to do a prediction, it will also predict better for this district income and test score situation. Let's say we want to predict the change of income from 5,000 per capita to 6,000 per capita, then we'll put 6 into this regression model. Okay, this is 6,000 because this is 6 because the unit is $1,000 per capita. And this is the y hat for $5,000. And the difference is 3.4. That means if you increase your income from, increase the district income from 5,000 to 6,000, then the effect on test score is 3.4. Okay. How about from 25 to 26? Okay, using the same techniques, you can see that from 25 to 26,000, the effect on test score is just 1.7. And from 45 to 46, the effect becomes 0. Okay. What does this mean? This means that $1,000 means different for different income values. For a lower income value, if you increase the district income by 1,000, then test scores can be changed for 3.4. But if you becomes reached all the way to the point of 45,000, then income doesn't really have an effect on test scores anymore. Or $1,000 increase doesn't really have an effect on test score anymore. Okay, so we achieve the linearity that we want to model. One important thing we need to be careful here. Okay, this is very important. I'm gonna test you in exam in some way. What if I asked you the effect of test score change from 65 to $66,000 per capita in terms of income? 65 to 66. If you look at this question, you probably will think, oh, I would just put 65 and 66 into this equation, and then I calculate the difference. Then I can have an idea about the delta test scores. But no, you cannot do that. And the reason is we cannot extrapolate outside the range of data. So the question is, what's the range of data? Okay, let's come back to our graph. Our graph has data points from, let's see, we have data points from around 5, right? All the ways to 55 or something. So this is all the black dots data range. This is our data range that all of our data comes from school districts that their incomes are between 5 to 55 or ish. Okay. So if you want to do a prediction out of this range, it doesn't make sense because you are trying to predict something that you don't have data to support. Okay, so that's called don't extrapolate outside the range of data. Okay, so if we extend our model into a cubic specification, so in this case, we have x1, x2, and x3. And so x1 is income, x2 is income square, x3 is income to the power of 3. So this is the results. And this is beta 1, this is beta 2, and this is beta 3. Is beta 3 necessary? Or is x3 necessary? We can take a look at beta 3. So beta 3 is significant at 5% level, right? Because p-value is smaller than 5%. It's exactly smaller than 5%. So in this case, if we use the standard, which is 5%, then x3 is necessary. The cubic term is necessary. But we can also argue that it's only a significance at 5%, not significant at 1%. So we don't know. If you guys have already watched the video of the previous chapter, we can actually also do a F-test for x2 and x3. Okay, this is x2 and x3. We can do an F-test. We can test whether x2 and x3 combined are necessary or not. So the next page is F-test. Okay, the F-test says that we want to test if income squared and income to the power of 3 equals to 0 can be rejected or not. and we end up having an F statistic that's 37. Remember that when F statistic is larger than 7 or 8, we can have a low p-value already. So in this case, 37 is way bigger than 7, right? So we end up having a probability that is 0.00. And this is the p-value for the F-test. Okay, so we have a small p-value, which means that we reject our null hypothesis. That's saying that income squared and income to the power of 3 combined are necessary or are significant. Okay. All right. So the conclusion is income squared and income to the cubic of 3 are necessary. We can put them into our equation. So let's take a look at the summary. In the summary, we have the polynomial regression as one of the approaches we can use to estimate a nonlinear regression that is very useful to see in, let's say, excess income, because income has one unit of income has different effect or at different level of income. So we can use polynomial regression. You can use a quadratic specification, or you can use a cubic specification, or you can have x all the way to the power of r. Interpretation is difficult. It's better you plot it out. Okay, this might show up in your multiple choice. So it is so it's difficult to interpret the betas. Okay, how do you say beta 2? How can you say, let's say x to the power of 2 increased by 1 unit? You don't know what that is, right? So to interpret a polynomial regression, it's better that you plot the predictive values as a function of x. Okay, and then you can also compute the predicted change of delta y at different value of x. So this is what we did in this table. We want to interpret what this equation means. So we calculated 1 unit change in income at different levels of income. Okay. And the second way is to plot it out. Okay. All right. So the hypothesis concerning degree R can be tested by a t-test or f-test on the appropriate blocks of variables. So if you're only testing x to the power of r, then you take a look at the t-test for beta r hat. If you are testing whether a bunch of variables, okay, a bunch of polynomial variables are necessary or not combined together, then you can do an f-test. And so that is how you choose the degree of R. You plot the data, you use T and F test, you check sensitivity of estimated effects, or you just use your judgment. Okay. All right, so that's everything about polynomial. Let's move on to the log functions. In this section, we have 3 different forms of log. I'm gonna move to the second page first, and then we'll come back to this page. We have 3 log regressions, which is linear log linear, and log. Okay, it simply means that which variable that you're taking a log of. So for example, in the first one, if it's a linear log function, then you do not take log of your y, but you take log in your x variable. Okay. Why do we need the log? So now let's return to this page. So the natural log logarithm of x it can be transformed into a percentage or elasticity term rather than linearly. Here is here's the process of how we transform it. I want you guys to really understand what this is, but some people probably might not have learned calculus. So I'm not going to require, but I think it's very important that you really understand this. So then in the later pages, you don't need to memorize things, because memorizing can, the problem of memorizing things is that you easily forget about them. Okay, but understanding things, you remembers it, because if you understand it, it stays in your brain. Okay. So here is the change in log. If we increase x by delta x unit, and then log x plus delta x minus log x can be written into one term, which is log of 1 plus delta x divided by x. Okay, and this term is similar or is very close to delta x divided by x. Okay, why is that? You can think of this is x and y. Oops, this is x. This is y. Oops. If you have learned, things like fx, oh, this is really difficult to write. This equals to log 1 plus x. Okay, if I want to plot this, first we can plug another one. Okay, first we can plug this one. So gx looks like this. This is g. But fx equals to log 1 plus x. So what happened is that gx horizontally will move 1 unit. Okay. All right. This doesn't really look like it. If you horizontally move gx by 1 unit, then you get fx. Okay. And fx is approximately equal to is approximately equals to y equals to x. It might not look very much the same, but the idea is that, so if x equals to delta x divided by x, then log 1 plus delta x divided by x equals to delta x divided by x. Okay. Another way to have an idea about it is this one. If you take derivative of log x to x, you get 1 over x. Okay. Numerically, log 1.01 is approximately equals to 0.01. Okay, so log 1 plus 0.01 is approximately equals to 0.01. In the same way, log 1 plus 0.10 is numerically close to 0.10. Okay, this is numerically. See, log 1.01 equals to 0.00995. If you round this to two places, then you get 0.01. The second one, log 1 plus 0.1 equals to 0.0953. And if you round this one, it's also sort of close to 0.10. Okay, so that's why we want that's why we have this nice thing about log, that is it sort of becomes the fraction of delta x divided by x. Okay, fraction of x, fraction of delta x divided by x. This is kind of like percentage change, because at this point you don't care how many units of x change happens. You only care how much fraction of x has changed. Okay, so if you feel confused, we're gonna take a look at these examples and go through the mathematics together. Okay. Okay, first one, linear log. Y is linear, x is log. Before you have, so this is the original term, we call it before. And this is the after, because we change x by delta x unit and y by delta y unit. Okay, so if x changed by delta x, y will change by delta y. And now we want to figure out what's the relationship between delta y and delta x. So we subtract after and before. In the right hand side, sorry, in the left hand side, there are only delta y left. In the right hand side, we have this whole thing, which can be approximate to this term. Okay, again, the right hand side, we have beta 1 times log x plus delta x minus log x, but because we know that it can be approximate to delta x divided by x times beta 1, we can now have an idea about what beta 1 means. So beta 1 means delta y divided by fraction of x that has been changed. Okay, so what does this mean? It means that if x changes by certain fraction, then y would change by certain unit. And if you divide them together, it equals to beta 1. Okay. Why do we need a small delta x? Because we believe that delta x is, okay, how do I say it? Small delta x means that when you learn derivatives, you want the derivative to be very small because you want to get the slope, right? So 1 unit change of x is a very small delta x, or even smaller. Okay. All right, so that's our conclusion. Beta 1 equals or approximately equals to delta y divided by delta x times delta x divided by x. Now 100 times that this term is equal to percentage change in x. So 1% increase in x is associated with 0.01 beta 1 change in y. Okay, I guess it is a little bit difficult to understand, but we can understand that in this way. So first understand this one first. 100 times that. So suppose if your x is 10, okay, I give you an example. If your x is 10 and your delta x is 1, then let's say increase 1 unit of x means that you change the 10% of x, right? So increase delta x, oops. Increase delta x means that you increase x by 10% because the original value of x is 10. Okay, so 100 times 1 divided by 10 is 10%. I think it's pretty straightforward. Okay, so I think this is very straightforward. Now you can now if you understand this part that I have circled out, then the next part is to understand why 1% increase in x is associated with 0.01 beta 1 change in y. This is how you can think about it. Delta y equals to beta 1 times delta x divided by x. Okay, let's say now it is 10%. But remember, what does 10% mean? 10% actually means 0.1. Okay, so it equals to 0.1 times beta 1. Okay, now you probably ask me, but it says 0.01, not 0.1. That's correct because my delta x is, sorry, because my delta x divided by x is 10%. Okay, so imagine if that part becomes 1%, if beta 1, if it becomes 1%, then how do I interpret it? Okay, if it's 1%, then numerically it is beta 1 times 0.01. Therefore, we conclude that 0.1%, therefore we conclude that 1% change in x is associated with 0.01 beta 1 unit change in y. All right, hope this is clear. I hope this is clear. Okay. All right, so if you understand, that's great. If you don't understand, then this line is what you need to remember. Okay. And remembering it seems easy, but it can be frustrating and you might forget it or you can memorize it wrong. So you better understand it. Okay. In the linear log population regression, 1 unit change in x, sorry, 1% change in x is related to 0.01 beta unit change in y. So the change in y is unit change, but the change in x is a percent change because we are looking at it in a relative term. We're looking at delta x divided by x instead of delta x. Okay. All right. Oh, there's example. Okay. All right, so when is it appropriate to use log in an income term? Think about income. $1 is different for poor people and rich people. Or you can say $1,000 is important for poor people, but not so important for rich people. And how do we make it more realistic? Then how about 1% of income or 10% of income? Right? You probably can argue that for rich people, 10% of their income is as important as 10% of income for the poor people. Okay. So for poor people, 10% of income could be I don't know how much. Let's say $500. $500 is important for a $5,000 income person, while 5,000 is as important for a person who earns $50,000. Okay, so in this case, percent of income makes much more realistic sense. And that is why in this case, using a log income term in this linear log model can be a very good model. So let's run it. Let's see what it looks like. We're gonna compare it with the cubic regression. So the linear log regression is the gray line, while the cubic regression is the blue line. We can clearly see that they looks very, very similar, right? And it's actually difficult to tell which one has a better R square. I feel that maybe the gray one has better R square, but it's really hard to tell. So you can argue that, okay, on the graph, they look very similar. Maybe both of them are good models. Okay, maybe both of them fit the model really well, except that for the log linear model, it's easier to interpret. You don't need to break down the income, and you can just say that, okay, certain percent change in income leads to certain unit change in test score. It's easier to interpret. Okay, so the conclusion is maybe both are fine. While the linear log regression is easier to interpret. Okay, and probably you can compare R square, right? To see which one is better. Okay, so then let's move on to log linear population regression. This one we have y that take log, but x is linear. Again, we have before, we have after, and then we subtract before and after, which we end up getting this thing. And if we move the beta 1 to the left-hand side and move everything to the right-hand side, then we have beta 1 equals to delta y divided by y over delta x. Okay. So how do we interpret this? Now we have y that is a percentage change in y, but x is a unit change. Okay. So this one equals to, you can think of it as 100 times 1%. 100 times 1% change in y divide by, divide by delta x. Delta x is still the same. So then if you have to move that 100 to the left-hand side, then you end up having this. Okay. So that means a change in x a change in x by 1 unit is associated with 100 times beta 1% change in y. Okay. Okay. Um, I think, okay, so this is what you need to remember. While these things, it's better to remember, it's better to understand, but if you really cannot understand, then you remember this part that I have highlighted. Okay. What are the units of U and SCR? The unit of U and SCR will be the same with Y. Okay. And so it will means a fractional deviation. This one is not required. Okay. All right. Let's move on to the last one, which is log. Again, you can read about it on your own. You have before, you have after, and you subtract before and after, which end up giving you this beta 1 is approximately equals to fractional change in y divided by fractional change in x. How do we interpret it? This one is the easiest to interpret. It means that when 1% change in y is associated with beta 1% change in x. Or you can interpret it in an extreme way, that is 100% change in x. Will lead to 100 times beta 1% change in y. Okay. But we don't interpret that in the same way, right? Because 100% change in x, how that if we usually don't have that much change in our variables. So it's better to interpret as 1% change in x is associated with beta 1% change in y. Okay. And in the log specification, beta 1 is what we call it elasticity. Okay. You probably have learned elasticity in your in your microeconomics class. I bet some of you have forgot about it, but that's fine. So elasticity exactly means that how much fraction change in one thing will lead to how much fraction change in another. It's all relative term. It's all relative in percentage term instead of an absolute term, that is how many unit change in your variables. Okay. All right, so there is also an example in log test score and log income. You can take a log of test score and you can also take log in your income. The problem is the R square probably won't tell you anything. Okay. So then you end up getting this one. The log linear function looks straight. And the log function looks better. Okay. Because test scores now is not linear anymore. See? So log linear, because test score is not linear anymore, so log linear becomes straight. Okay. Might be confusing, but that's fine. I don't test you on anything about it. But log is still a curvy because your y-axis is, sorry, your x-axis is still absolute term. Okay, so which one fits better? I think log fits better. Okay, so that means if we increase 1% in district income, we probably end up having certain percent change in test score. Okay, and then that depends on your estimate. Oh, the estimate is here. Okay, the estimate is 0.05. Okay, so 1% change in income will lead to 0.05% change in test scores. Okay, that's how we interpret this one. All right. In summary, log transformation, we have 3 cases. You need to remember the name of these 3 cases, what the regression function looks like, and how do we interpret the beta in all of 3, okay? In log linear, it's 1% change, sorry, in linear log, it's 1% change in x leads to 0.01 beta unit change in y. In log linear case, it's one unit change in x leads to 100 beta percent change in y. And the log model, it's 1% change in x leads to beta 1% change in y. Okay, you need to remember all of these if you cannot understand. Okay. So when do we choose the specification? You can be guided, it can be guided by judgment or tests. Okay, you can do tests and definitely you can plot the predicted value. That's the most easier case because looking at graph, it's probably the easiest way to have an idea about which model works better. All right. There is other nonlinear functions, but this is not required, okay? This one, exponential, negative exponential growth, not required. It seems like negative exponential growth regression still fits really well. Okay, even better, I think. The blue one seems better than the gray one, right? Okay. All right, so that's it for the first 2 sections. I record another video to talk about the interactions, and we will spend more time here because this involves different variables. Okay.